Hello, this is Leo. Today we're going to talk about this question that's asked by Amazon and Facebook recently. This is a Leetcode premium hard question, and I promise you by going through this video, you 100% understand this question. In modern English word, we have the letters that it's following by alphabetical order. And we know that if we are looking for single letter, we have A, B, C, D until E, and that's the alphabetical orders for a single letter. What about we have multiple letters in one word? For example, we have A, B, and AC. The order is that if the first letter, they are the same, then we are looking for the second letter. So in this case, B is above C. So we have AB at first and then AC. If you are looking for DE and HJ, by looking at the first letter, we know that letter D is above H. So we put DE above HJ. So the rule is no matter how long is the word, by checking out the first letter, if they're different, then this whole word be determined by the first letter that's different. Let's look at the other example. We know that CCCD is above CCCH because we don't care about the first three letters because they're all the same. The order that is different between those two words is determined by this different that's at the fourth character because D is above H. There is another example that this word is above this word because we don't care about the rest of the characters that it's behind the first different letter. So if D, we know that D is above H. Now let's forget about the English modern alphabetical order A, B, C, D until Z. Let's look at this alien dictionary that now we don't know the order of those letters. So if we're looking for this order of words, what information can we get? Well, let's check the first 1 and 2. We know that WR and WR, they're duplicates. So by checking the third element, we know that in this alien dictionary, T is above F. So let me just get a direct graph that T is pointing to F. That means we can go to T first and then F. Let's move on by checking the second word and the third word. The first letter, they're different. Now we can say that W is above E. Next, by checking the third and the fourth word, the first character is E, so they're the same. By checking the second letter, we know that letter R is above T. Next, by checking the fourth and the fifth element, we know that E is above R. So starting from W, we have W to E, E to R, R to T, and then T to F. Finally, we return these orders in one word. If you understand what I just illustrated before, now for this example, we know that we have the graph like this. So Z points to X, but X points to Z. So we have a cycle. There's no way that this order makes sense. So now we return a null value. There is an edge case that we need to consider. In modern English word, the good is always before goods. So by going through all the letters, if, for example, A and B, we know that the first two, they are the same. And we cannot go to the third because the first, it has fewer length than 3. Then AB, it's always above ABC. So if you have a word that is AB, and we have the second word that is AB or something, no matter how long is the rest of the letters, the one that it has the fewest length always shows at first. It sounds like a pretty complicated problem. Let's break the problem into several sub-problems. The first step is how to build the graph from the arrays. The way we build the graph is relating to our next step, how to find the cycle. So in this case, I'm going to choose the topological sorting. The topological sorting is for directed graph. So I need to declare a graph variable to have the nodes and the edges. We also need to come up with another in degree to specify how many edges that goes into one node. If you are not familiar with the topological sorting, you can check out my previous video. It has the median Leetcode question about it. There are use cases that we are not sure about the order of the ladder. For example, if we have AB and ADC, we know that B is before D, but we're not sure about the order of C. In this case, C can be in any order, but we still need to return C. Therefore, we need to scan all the given ladder. Initially, we scan all the ladder in the array. In the graph, here's what we built from the current node that points to its downstream. Therefore, we need to have the array because each node can point to multiple downstream nodes. And the way we initialize the in degree dictionary variable is that we put each node as 0 in degree at first. We will later then update these two variables. Every time we are comparing the current word and the next word. And we need to scan the letter inside them. At first, we have W and W, they are the same. We're moving to the next letter. R and R, they are the same. T and F, they're different. That means T is above F. So that means T is pointing to F. Inside the graph variable, we find the key that is T, and then we put F inside. Now we know there is an edge that it's pointing to F. That means the in degree of edge is 1. It's going to be add up to 1. We are moving to the next element. By comparing the second to the third, we know that W is above E. So we put E inside the graph that has the key W. And then we increment the in degree of E by 1. Next, we are comparing the third element to the fourth element. We know that R is pointing to T. So we add T here. And then we increment in degree of T by 1. Next, we are comparing the fourth to the fifth. We know that E is pointing to R. So we add R here. And then we increment the in degree of R by 1. So we come up with the word that WERT. The in degree of W is 0 because this is the starting node. The graph is for so we come up with the word WERTF. The in degree of W is 0 because this is the first letter. It doesn't have any edge that comes into the letter W. And the F is in the last letter. So that means it doesn't have any edges that coming out of F. And this is the Python code. I strongly suggest you pause here for a minute or two to understand everything so far, and then to see if you can come up with a different solution. First, I declare those two variables as a dictionary variable, and then I declare two functions to simply just add the node to the graph and increment the value into the in degree variable. I have the nested for loop here that at first I'm scanning each individual word. Inside the variable, I have another nested variable to scanning the letter inside each word. If there's a new letter that it's never been added to the graph and integrate variable before, then I just simply initialize an empty array that means the edges and then integrate to be 0. I need to scan the entire array one more time. This time I scan up to the second last element because every time I'm comparing the current word to the next word. So that's the reason I is in the range length words -1 here. One thing to keep that in mind is that we need to find the minimum length between the current and the next word to avoid the index exit. At J index, if the current word is different than the next word, that means this node needs to be added into the graph. There is an edge case, I discussed it before. If we have AB, JD and AB, because I specified this before, AB should be above ABJD. In this case, that means the result is invalid, so we need to return null. We are halfway through the problem. The next step is to implement the topological sorting. If you remember how the algorithm works, the first step of topological sorting is to add the in degree that is 0 to the stack. This time we add W into the stack. As we pop from the stack, we add it to the visited. Now we need to get rid of the node W in the graph. When looking for the graph variable, we know that W is pointing to E. So we need to refer to the in degree variable to find E as well, and then decrement by 1, so now it becomes 0. We now have another in degree that is 0, which is node E. We add it to the stack. We get rid of E. When looking for graph variable, we know that the node E is pointing to R. So we decrement the in degree of R to 0. And then we add R into the stack. We pop E from the stack and add it to the visited. Now we pop R from the stack and add it to the visited. Then we need to get rid of R. We find that R is pointing to T. So we decrement T to 0. Eventually, we visit all the nodes in the graph by order and we return the result. If the number of visited is less than the number of nodes we have, then we need to return null. It's simply because if you have a cycle, that means the in degree of each node is 1. That way we cannot add any of the nodes into the stack, so we have a fewer number of visited. Here's the Python code for topological sorting. Instead of a visited array, I declare the result variable as an empty string, because at the end we need to return the result string. This is how I append each letter to the string. Because we may have multiple nodes that it has in degree 0. For example, we have the graph that A points to T, but the node D and W, they're individual node. It doesn't have any edges that attach to it. So that's the reason I need to look through all the nodes in the degree and find out all the in degree 0 node. In the end, if the length of the result string is equal to the length of the in degree, that means the number of nodes we have. That means we already visit all the nodes and we can just return the result. Otherwise, that means there's a cycle and the topological sorting are missing some nodes. Therefore, we return the empty string. If you like this channel, please click like and subscribe. Thank you.